Hi everybody, and welcome back. This is going to be the beginning of chapter 11. Actually, did I delete that? Maybe I didn't even write it on there. Sorry. This should say chapter 11 right here. Uniform circular motion. And this and the last chapter, chapter 12, are going to be similar. That is dealing with things either moving in circles or dealing with gravity, which kind of has a circular component to it. But I'd like to start off this chapter. Well, actually, let me go back. The last chapter, chapter 12, will probably abbreviate a little bit, but we'll spend most of our time focusing on chapter 11 right here. So make sure you understand this stuff because that'll kind of lay the groundwork for chapter 12, the part of it that we do. So, all right, I'm going to start off this chapter by showing you a couple different pictures. All right, and seeing if you can kind of figure out what's going on with them. So this is the first one right here. So what's happening right here? Well, I'm not sure if you can tell, but the wall is kind of curved right here. All right, from there to there, and we seem to be in kind of this radial pattern. Well, this is the inside of one of those. I guess you would call it the rotor or the Gravitron or something like that. That is a spinning cylinder, you might say, where if you stand up against the wall, you're pressed against the wall, and in many cases, the floor drops down, so you're not actually supported by anything other than your own friction with the wall. Well, if you've ever seen this, I don't know, look away because horrible things have happened when people try to do this. This is tremendously stupid, but it actually is taking advantage of physics. This guy's actually standing up on the wall, and the same forces that are forcing that guy and this guy and this guy against the wall is actually forcing this guy down on the floor. And so conceivably you could, well, or obviously you could stand up and be in a standing up position horizontal to the floor, or that is parallel with what was previously the floor. Like I said, I really do not recommend trying this at home or at any other location for that matter, but that's what's happening right here. So the question is, what's causing that? And let's see if I can delete all this here. Okay. Well, we have a force. While everybody feels pushed to the outside, there's this force. Let me change my little laser pointer here so it's in a different direction. Well, this guy feels pushed to the outside, and he feels pushed to the outside, and everybody's feeling this force to the outside. It's not a real force. There's a force that is acting towards the center, and this force right here, acting towards the center of this circular room, is what is keeping this guy on the inside of this loop right here. There's a similar force acting on this guy towards the center, this guy towards the center, and they're feeling that force on their backs. That is, it's a force from this wall right here. If this is a circular room and this room were spinning around, if there were no back wall right here, these guys would go flying out into the parking lot or something like that. It's the actual strength of this wall, and you can see this pretty sizable beam right there giving the wall its strength. The wall is really directing a force towards the center of the room, which is keeping these guys feeling like they're stuck to the wall and keeping this guy standing up. If the wall were to suddenly break, he would go flying out through the back of it, like I said, into some other part of the amusement park. The similar drawing or a similar picture is going to be this one right here. You've probably seen this happen before, where you have somebody who has to stay inside this fairly small circle, all right, but they whip around some heavy weight. This is, I believe, called the hammer throw in the Olympics or in the World Championships. All right, well, this hammer, all right, if you're in that hammer, it's called a hammer right there, that ball, you feel like you're being pushed to the outside, right? But what's really happening here is, let me see if I can erase this thing. No, I can't. Erase that right there. What's really happening is the person who is causing the hammer to swing around is directing a force towards the center. All right? And every which way she turns, she directs it towards the center so that it causes this hammer, this weight right here, oops, there, to stay in a circular path until she finally lets go of it, and then it goes flying off, and then that's part of the competition. All right? But this is similar to this right here in that there is a center-directed force. Or we should actually say a center-directed acceleration, because that force is acting on this guy's mass and this guy's mass and this guy's mass, and force that the athlete here is applying is acting on this mass right here. And so we know that a force acting on a mass is a result of an acceleration. So really what we're going to be calling this center-directed value is centripetal acceleration. Centripetal acceleration. So you've probably heard of people say centrifugal force. It's not an actual force, but centripetal means center seeking, towards the center. So that's going to be kind of the groundwork for this whole part of the chapter. Some sort of force, some sort of acceleration that's directed towards the center of a rotating body. So that being said, let's define some of the parts of a circle, objects moving in circular motion. All right, so anything directed towards the center, we call it the radial direction. Like that, that's all the radius right there, all right? Well, say maybe we have an athlete spinning around a hammer or something like that, or whatever you call that ball. It's moving around. There is a, so it's going around in this, we'll say in this direction, okay? The force or the acceleration is being applied radially. That is, you keep having to pull inwards towards the center to keep that mass in a circular path. But really, the mass wants to fly off out into space in what we would call a tangential direction. That's tangent. That's tangent. Any line that touches a circle at just one point is tangent to that circle. So we call that the tangential direction. So we can have two measures of motion here. We can have the velocity at which it moves around the circle in an arc. We will call that angular velocity. We'll talk about that in just a minute. Or you can also have tangential velocity, where whatever that speed is, or whatever velocity is, if you let go of the string or you let go of the hammer, that thing flies off now in a straight line with that very same velocity that it had in a curved direction when it was spinning around. What's interesting though is that since an object that is moving in a circle, so here's our, all right, there's our circle right there. We'll have an object that's, well, let's say red, okay? Well, the velocity constantly changes. There's a velocity, there's a velocity, there's a velocity. Now the value may be the same, but you can see that the direction of the velocity is changing. So whether it's the magnitude or the direction changes, doesn't matter. It's a different vector. So anytime you have a change in velocity, whether it's the magnitude or direction, you're going to have an acceleration. And acceleration is responsible for keeping this object in a circular path. Otherwise, it'll want to move off in a straight line. So at any one point right here, so say this object is right here, or right here, or right here, or right here, or wherever. At any one instant, the instantaneous velocity, the velocity is directed in a tangential direction. That's how I've drawn all these velocities right here, as kind of tangents to this orange circle, this orange arc. All right. But again, this velocity, even though it's the same magnitude as this, it's a different direction. And so that different velocity vector is going to be the result of an acceleration that's directed towards the center of that arc, or towards the center of that circle right there. So the acceleration, if we move towards the center, and let's see if I can, oh, there we go. Towards the center, we're going to call the negative direction. That's negative. That's negative. That's negative, and so forth. Towards the outside, towards the rim of the circle, we're going to call that the positive direction. So the acceleration is always directed towards the center right there, and that's that centripetal acceleration. I'll draw that in blue right here. The centripetal acceleration that I mentioned before, that the hammer thrower is pulling towards the center. The walls of the gravitron are holding the guy in place because of their strength, pushing him towards the center so he doesn't fly out in a straight line. So that's the acceleration that we're going to be talking about over the next chapter. So this actually brings us to the concept of uniform circular motion. If you have a constant acceleration being directed towards a central point, all right, or a centripetal acceleration, and no matter where the object is around that central point, the acceleration is directed towards the center, we will say that object will have uniform circular motion. Uniform meaning that it is moving around in a circle at a constant speed. I really can't say constant velocity, right? Because the velocity keeps changing because the direction keeps changing. But a constant speed. Right? It follows a circular path. And what's causing that is this centripetal acceleration. Centra, you can probably figure out, means center. Petal means seeking. All right? Directed towards the center right there. So this acceleration acting on some sort of a mass, I'll do the mass in green, I guess, all right? So this mass is right there, that mass is right there. In order for that mass to be accelerated at that rate, it's going to require a certain force, and so we call it the centripetal force. But the force is really a result of the mass being multiplied by the centripetal acceleration. I'll put that as a C right there. The centripetal acceleration that it's experiencing. Okay, so as objects move around in a circle, you can't go far in a circle without repeating the same path over and over and over. And if something has uniform circular motion, it is in fact repeating a cycle. All right, it's going around the same path over and over and over again. So we can talk about this in terms of two things, for lack of a better term: period and frequency. Now, these are actually very closely related, just sort of in an inverse manner. Period refers to a time period, and that's why period is indicated by a capital T. I'm going to circle that right there. Don't think of it as P and that, and P is power or momentum anyway. So think of it as time period, all right? A time period, and that's why we call it a capital T, all right? It's the amount of time it takes for one cycle to be completed, all right? So however long that takes, well, let's say, I don't know. I'm going counterclockwise here, but let's say these are hands of a clock, all right? Well, this thing is, the minute hand goes around the clock face once every 60 minutes, right? Once every hour. So that would be the period of the minute hand. By contrast, frequency is the inverse of that. It's how many cycles or how many times around you can do per unit time. Now, our unit time is seconds. So it's cycles per second. It could be any unit time, but we're going to do seconds. And the accepted notation, the accepted term for cycles per second is something called Hertz. Now, usually that's used to measure waves or sine waves. That's a bad sine wave right there. But try that again. All right. Up, down, etc. All right. It's how many waves, this is like a cycle right here, 1 wave, 2 waves, 3 waves, move past you in a second. All kinds of radio frequencies are measured in hertz and megahertz and gigahertz and that kind of thing. All right. Well, we're not going to measure things in that fast of increments, but we're going to have something carrying out a cycle, that is a cycle of motion. Do like a little red ball right there. A cycle of motion in a certain amount of time. So we're going to be talking about cycles. A cycle has a certain amount of time, period. Or the frequency is how many cycles you can get per time period. And so they're really inverses of each other. Time is 1 over the frequency, and the frequency, and we do call that a lowercase f, is 1 over the time. For example, let's see, we'll go back to the minute hand going around the clock. All right. Well, the time, that is a time period, would be 60 minutes, or if that is 3,600 seconds. All right. That would be the time period. The frequency, that is how often it goes around. All right. So the frequency being 1 over the time period would be 1 over 36 hundredths of a second. So do I have that? Or time period is 3,600? Yeah, I think so. Because so that's like saying one cycle, or one complete loop, as it were, every 36 hundredths of a second. So the frequency would be, let's see, 1 over 3,600. That would be 2.7 times 10 to the negative fourth cycles. Per second. All right, if we were to take this right here and boil that down, that means, all right, so if we have a minute hand going around a clock once every 3,600 seconds, 60 seconds times 60 minutes, right? Okay, that's our time period. Our frequency would be, how many cycles does it carry out per second? Well, not one cycle, not a half a cycle, but a very tiny fraction of a cycle every second. So every second that ticks, I really should have drawn this clockwise instead of counterclockwise, sorry, but every second that ticks by, it goes 2.7 times 10 to the negative fourth of the way around one cycle. Does that make sense? I may have picked a bad time period right here, but we'll say if something is a matter of, we'll say 10 cycles per second. All right, so this is a lot faster. So something happening 10 times per second, that would be your frequency. All right, what would the time period be right there? Well, it would be the inverse of that. It means that if you've got 10 loops per second, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all in 1 second, then that means one loop or one cycle, the time period for that would be 1/10 of a second. All right, so that's how frequency and time are related. They're simply inverses, or I should say frequency and period, or time period, are related. They're simply inverses of each other. Okay, so like I mentioned, that there are units for frequency in Hertz. That is cycles or loops or completions of whatever is happening repeatedly per second. That's denoted Hertz, Hz, which is short for Hertz, which is somebody's last name. So that's cycles per second. But one thing you may be familiar with is RPM. That's revolutions per minute. All right, that's the P. That's where P comes from. Revolutions per minute. All right. Well, if you want revolutions per second or cycles per second, you're going to need to convert this by let's see, we would by multiplying by 60 seconds, or the other way around if we're going from seconds to minutes. All right, so let's convert 45 RPM to Hertz. All right, 45 revolutions per minute. And we want to find out how many revolutions per second that would be. All right, so 1 minute, we're doing factor labeling right here, 60 seconds. And there we go, so 45 divided by 60. Oops, that's 445. 45 divided by 60, did that again, that's all right, is 0.75. 0.75 Hertz. All right, because we converted the minutes to seconds. We're still talking about cycles or revolutions. It's all the same thing, but the time period is really what's different. All right, whatever is being repeated is the cycle or revolution. So this brings us to the concept now of centripetal acceleration. Here you see it shown as an ACP. I usually just indicate it as an A sub C. All right. But that means centripetal acceleration. It's not directed in a straight line, but it's directed radially inward. It's directed towards the center of a circle. So there's our object moving in a circular pattern. All right. AC, AC, etc. All right. And so our equation for this is going to be v squared over r. And what r is the radius of the circle. That's really going to be important. You know probably that, let's see, if you go around a curve in your car, it's much harder. It requires more, it creates more g's, more side acceleration if you go around a curve at a certain speed with that kind of radius. That's not very good. There we go. With that kind of radius right there versus if you go around, it's much easier with a bigger radius. So the size of the radius definitely matters. And that would determine how much centripetal acceleration is required to be directed towards the center to keep you in that curve or keep you in that arc. All right, but velocity plays a big part as well. Obviously, you can go around a corner much more easily if you're taking it easy or going slow than if you have a high velocity. It requires much more centripetal acceleration to go around a small arc at a high velocity than a big arc at a low velocity. You can take your good old time going around this big arc. Velocity and radius really kind of work against each other right here in a small arc at high speeds. So of course, velocity is the object's speed measured in meters per second. And of course, r is the radius. We just simply measure that in m. It's just a distance. We measure that in meters. So the direction of the centripetal acceleration is always going to be changing. Why is that? Because the you might say the towards the center, the negative r direction, and see this little hat right here? That's r hat. That is the radius direction. Well, this centripetal acceleration is directed towards the r hat direction. We had x hat and y hat. And this is being directed here in the r hat direction, as is this here. So all these are the r hat directions, but the direction keeps constantly changing. Actually, I should really put the negative r hat, negative, because towards the center is negative. But that means that the direction of the centripetal acceleration is always changing. Okay, so what I'm going to do is I'm going to take this equation that we have right here, and this was simply just given to you. We're not going to derive this, but we're just going to take this at face value, and we're going to combine this with another equation that I hope you'll find familiar in order to get equations to calculate centripetal acceleration when you need to know things like frequency and time and that kind of thing. So I'm going to start actually with the next slide being blank right here. So if you don't have the next a blank sheet on your page, or next a blank page in your notes, just get a blank page, and we're going to do a little bit of deriving right here. So the circumference of a circle. It's not a bad circle right there. The circumference is the distance that an object takes to go around a circle, right? And velocity equals, we're used to saying displacement over time, right? Well, we're not displacing something in a straight line, we're displacing something in a circle. So what we should really say is circumference over time, right? The velocity this object takes around a circle is the circumference over time. And of course, we do know that circumference, or hopefully you remember from math, what is our equation for circumference? That's 2 pi r, right? 2 pi r. So our velocity will be 2 pi r over time. So we're going to take this and say that's going to be important to us in just a bit. Okay. How would we take that and turn that into frequency? Well, if you know frequency, if you recall back from a slide or two ago, frequency is simply the inverse of time. That's just like saying velocity is also equal to 2 pi r what? Well, in the top one here, we have t in the denominator. So that means frequency being the inverse is simply going to just come up right there. All right, frequency is your cycles per second. Time is simply your time period in seconds, but it's in the denominator. But it's basically telling you the same thing. All right, so these two are going to be our equations for velocity. And if you recall, let me go back a second. We have velocity right here. We're going to stick those equations for velocity in there and come up with new equations for centripetal acceleration that account for like frequency and time and all that other stuff. All right, so I thought about doing this on a different slide, but I might be able to do it just right here. Let's see. Oh, I know. I'll just shrink this down. Give us a little bit more space there. Okay, so let's turn this into equations for centripetal acceleration. Centripetal acceleration in this case, that's not going to help. There we go. Centripetal acceleration is v squared over r, right? So with this right here, we can say, let's take that v and stick that in the v squared. So that would be what? Well, that would be 4 pi squared r squared, right? Because you square the 2, you square the pi, and you square the r. All that over t squared, right? Because the t in the denominator gets squared. All right? Okay, but remember, what we just did was we squared just that velocity right there. Don't forget that there was also an r that was originally in the denominator right there. So that is going to go down here in the denominator as well. That's the original r that was right here. All this other mess right here is this velocity squared. Okay? So, what does that mean? That means that we can actually cancel out one of these r's right here and simplify this to our acceleration being 4 pi squared r, that's a pi squared there, sorry, over t squared. All right, and that is going to be our one equation for centripetal acceleration. Let's do the same thing for frequency, and then we'll call it a wrap. All right, so centripetal acceleration velocity is also 2 pi r f, right? We also know that centripetal acceleration equals v squared over r, right? We just said that a minute ago. So let's take and let's square that v. So we square the 2, we square the pi, we square the r, and we square the f. So that's going to be 4 pi squared r squared f squared right there, right? That whole velocity squared, all over r. All right, fair enough. Once again, one of these r's cancels out, and so our final equation is going to be 4 pi squared r f squared. And that's going to be our final equation. All right, so that right there is also centripetal acceleration. These are both essentially the same thing, except once again, the f squared and the t squared, they're inverses of each other. So one's going to be in the numerator and one's going to be in the denominator. All right, I think I've gone on for quite long enough for now. The next video, we're going to actually start some examples, but hopefully this has made sense to you. And if it doesn't, we'll just try to follow along as best you can in the examples. But if you do have any questions, make sure you contact me or come see me, and I'll be sure to help you out. Thanks for following along. I'll see you on the next one.